Thank you so much. Hi, everyone. It's great to be here. My name is Charlotte Tumescheit, and I'm a postdoc with Jenna Hastings at University of Zurich. And we are in the Institute of Implementation Science for Healthcare. And so we care about metabolomics and metabolism. And metabolism is at the center of health. And there are so many different factors that affect metabolism. Just to name a few, like what we eat, what we drink, our lifestyle, drugs we take. And so it's a really complex system, and we don't really fully understand it yet. And existing research has some limitations. And so we're going to take a step back, and we just want to look at the molecules themselves and their properties. Some applications here are we want to characterize newly discovered molecules, or we want to investigate candidates for drug design. And some of these properties, for example, are aqueous solubility. And you want the drug to be soluble but not too soluble, and also toxicity. You don't want it to be toxic, obviously. And so many machine learning methods are already out there to investigate these. Can you hear me okay, actually? Oh, okay. Thank you. Didn't lean forward too much. Okay. And these methods can really inform us about these new molecules and are really useful. However, they are not incorporating prior knowledge that much at the moment. And we have a lot of prior knowledge available in ontologies. And so our plan was to bring them together to improve property prediction. And in order to do that, the idea was to add an ontology pre-training step between the classical pre-training and the fine-tuning. What does this look like? Just a quick overview. The goal is to enable the model to benefit from the knowledge that's represented in the ontology, and then to turn it into a task where we can predict membership within the ontology. And then we can use this to hopefully have the model learn the features that are relevant for the domain, and also to learn quicker and just work for a wide range of applications. So as you can see here, I don't know if you can see, okay. So we first have the general pre-training, then we have the ontology pre-training, and then we do the fine-tuning. This is based on, so everything I talk about today is an extension of the work that already has been done by Martin Glauer, Fabian Neuhaus, Tim Mosakowski, and Jenna Hastings. And they showed that this method improves poison prediction, so that they use Tox21, which is a data set for toxicity prediction. And they could show that it does not only improve performance, but also stabilizes the training, makes it shorter, and also improves interpretability. And now the goal was to extend this to other applications. So toxicity prediction, that's a classification problem. And we wanted to see, does it work for regression problems as well? Does it work for different types of problems? To do this, we are using SMILES. And not sure if you're familiar with that, but it stands for Simplified Molecular Input Line Entry System. And it's just a way to describe molecules into a short string. So here, I don't know if you, okay, so here we've got caffeine, which with its corresponding SMILE string. And that makes it a great candidate for language-based models. We use, for our pre-training, we use two data sets. We use PubChem, which is a database for everything chemical, and we use the KBN ontology. So we use the Electron model, which is based on the famous transformer model, and an extension of the common mask language task. And so we built a Python library, which is called CapAI. If you want to check it out, there is a QR code. And it includes data sets that we extracted from KBN PubChem and supports pre-processing of chemical data, and also provides a training environment. And it also includes Cabify. And I just want to quickly do a cheeky advertisement for our newly updated version. Cabify helps you to classify molecules in Cabi. And we just had like an update. We have more models and a better interface, and you can now use pip to install it. And also, if you saw Chris Mangel's talk yesterday, he talked about generative AI, and it incorporates his work in this domain. And there's also a web server. So also here again, there's a QR code if you're interested in that. But now let's get back to our main topic. So the training pipeline for this method starts with the standard pre-training. So here we have 200,000 molecules from PubChem, and we do self-supervised training from scratch at first. And here, hopefully, the model learns the structure of the molecule. Then the second step, we take this model and then train it further on the ontology. And here, it's a multi-label classification problem. And we hope that the model learns the semantics of the tokens. And this is then followed by fine-tuning. So it's really your classical pre-training fine-tuning pipeline with an additional step. And the ontology pre-training, to go into a bit of more detail, we use a subsumption hierarchy that is within KB, and we turn it into a classification problem. So we take all the subclasses that have at least 100, all the classes that have at least 100 subclasses and have a smiles attached. And then we get basically a file of over 185,000 smiles, and each has 997 classes. And then we use this to train the model. And now we want to see if it actually works, if it helps. So our experimental workflow for that is as follows. First, we do the standard pre-training and get a standard pre-trained model. Then we use that to do the ontology pre-training, and we get the standard plus ontology pre-trained model. And then we fine-tune both models on the same data sets. And also here, for all the models, we use the same parameters, everything's the same. So it's really a fair comparison. And then we compare standard pre-training versus ontology and standard pre-training. We do this so we started out with solubility data sets, and there we used a curated collection of many solubility data sets, and we also used a bunch of data sets from MoleculeNet, which also has a solubility data set, but it's much smaller. So to give you an idea, we really tried to see, does it work for binary classification, multi-label classification, and regression? And here you can see all the data sets we tried. So we have different types here and different sizes. I mean, they're still quite small, but yeah, we try to get a variety of size and types. And we have, for example, the toxicity we already did previously. We've got binding results for a set of inhibitors. We've got solubility, lipophilicity, adverse drug reactions. So we really wanted to test this on a variety of problems. And the results I will now show you for each task type separately. First, we have the results for the binary classification. So on the left, you can see the F1 score, how the F1 score develops during training for the validation set. For base. And as you can see, the training is more stable if we add the ontology pre-training step. So you can see in turquoise without the ontology pre-training, and in purple for adding the ontology pre-training step. And then for the test results on the right, we tried for different metrics, and we can see that for these two cases, base and BBBP, it doesn't make such a big difference to use the ontology pre-training. However, if we now look again at toxicity and ClinTox and CIDR, we can see that in many cases for many metrics, we do see a big improvement. And again, we also see faster conversion in the training. And for the regression, here we've got the RMSE, the root mean square error. Keep in mind, we want that one to be low. And then we've got the coefficient R square, we want that to be high. So here we can really see a huge improvement in all cases if we use the ontology pre-training. Not only is the training more stable, so you can see again on the plots. So here can see for not using the ontology pre-training. And it's really like, yeah, it's not as stable as for the ontology pre-training. And yeah, also on the test results, we always perform better. Now, as a conclusion, so we improved performance in many cases, and we didn't need to do any feature augmentation. And we could see that the training was much more stable and also faster. And this method is, you can generalize it to other applications as long as you have a link between the ontology you are using and your data. And yeah, it's a very easy out-of-the-box usable method and to easily incorporate expert knowledge. And depending on the task, it does not always improve performance. So that's one of the limitations. But also the molecule data sets have their challenges. And in the future, we would like to investigate more applications and also more ontologies. And if you have any examples, we would be very excited to collaborate on that. If you have any questions, I think we have a lot of time for questions, rushed through a bit here. And would like to thank everyone involved in the project. And yeah, Jana, Till, Fabian, Martin, Simon, all involved in this project. And special thanks to the Hastings Lab, to Martin Larald as well, and to you for listening. And preprint is coming out soon. But in the meantime, you can go ahead and check out Cabify if you're interested in classifying your molecules. Thank you very much.
So, thanks for the talk. I have actually two questions, please. So the first one, could you please elaborate more on how the task is defined on the ontology pre-trained stage? The second question, was those stages done in a sequential manner? So the first stage, then the second, and the third, or was it done all together, one shot? Thank you.
Thank you for your questions. Yes, so the second question, yes, it was done in a sequential manner. So we first do standard pre-training, then we do the ontology pre-training, and then the fine-tuning. And your first question was, I think, to elaborate more on how the task is defined. Right, so it's also a multi-label classification task. So you have a number of smiles, and then you've got 997 labels, which correspond to classes in KB. So it's basically a classification problem of you take the smiles and want to classify its classes, so class membership. Exactly. Thank you for your questions.
Thank you for your talk. I have two questions. First, in these two pre-training steps, did you try experimenting if you skip the first step and you just do the ontology pre-training, or if you switch them around and do the ontology first? Is there any significant or meaningful difference? And then the second question is, if you compare it to any of the famous deep learning molecular embeddings like Mole-Former or these language-based models, and if you are planning to use them with the ontology pre-training to see if it will improve those models as well.
Great question, thank you. Actually, so the first question, we did not try that. It's a good idea though, maybe. I think the main point was because at first with the standard pre-training, we learn the structure of the molecule, right? We get an idea what a molecule is. And then the ontology, that will add the semantics, that will add some more context. So I think, but it would be interesting to see if we do it the other way around. Thank you, it's an interesting idea. And for your second question, I'm so sorry, can you remind me of your second question?
Just about comparisons to the other.
Right, thank you, yes. So we have compared it to the state of the art and also similarly working methods, and we do sometimes outperform them, sometimes not. However, we have not finished the benchmarking itself, which is why I haven't presented it yet, but it will be in the preprint if you're interested in that. And also we're actually working on also using GNNs and combine them with this approach to get hopefully even better performance. Thank you.
Yeah, so is your pre-trained plus ontology trained network bigger than just the pre-trained one? as in it has more hidden layers because you've added the ontology pre-trained bit?
That is a really good question. Actually, I did not check if it did.
Your diagram
I would
kind
have
of
to check
implied
that.
your diagram implied that the ontology bit is some extra layers.
Right. I mean, the number of layers actually stays the same for each step, if I remember correctly. I don't think but I would have to double check. I could get
You
back to you
pre-train the
later.
network, so you're essentially fine-tuning twice. So
Basically, yes.
Okay.
Yes, you could see it that way.
okay, cool, great, thank you.
Thank you.
Any other questions?
Sorry, I am just confused. Like, what is the end result? You're trying to predict the toxicity value, or you're trying to classify things?
So that depends on the task. So for toxicity, we try to predict different if they are toxic or not. So there are 12 labels. So that's the classification. And for other, for example, the solubility, that's a solubility value. So that's a regression problem.
So it is like along with the smiles, you're giving this ontology classes, and it is improving these predictions.
Sorry, can you repeat that?
So I'm just trying to get what you're telling. Like the input is the smiles.
Yeah.
We are adding the ontology classes as a new feature kind of thing, and this improves the prediction of whatever is the end result.
It's not really a feature. It's another training step.
Okay. Thank you.
Sorry, does that answer your question? Thank you.
Okay. So maybe I have one very last question. So as you show on this slide, CAPI is more than just a subsumption hierarchy. It has other kinds of axioms, functional parents, parts, and so on. Have you used any of those? And if not, do you see any use in them? Or do you think it's just enough to have a big hierarchy?
So that is a good question. Yeah, we have not used. So we only focus on the subsumption hierarchy at the moment, and we only want to have those classes that have 100 subclasses, and we only take the ones that have a smiles attached to them. So, yeah, it would be interesting to see if we can incorporate more. But that is a good point. I would have to think about. Thank you.
Okay, so thank you very much.